Ah, that's right. All right, so we're in section 6.2. Yeah, you probably see a lot of cosines in geometry as well. I know my geometry students we have in the past done a little bit with law of cosines. Let's recap really quickly the law of sines, when we use the law of sines. So we use the law of sines when we have, our easiest cases are when we have two angles and a side. So angle side angle, or angle side triangles. And we know that we only get that those give us unique triangles, so we always end up with one triangle. And then we have the possibility for the ambiguous case when we have a side-side angle triangle, and we can have 0, 1, or 2 triangles. So side-side angle is a case where we have to be careful. We have to check to make sure that we actually end up with a triangle. We're going to use the law of cosines for two other kinds of triangles. We're going to use the law of cosines for a side angle side triangle and for a side triangle. And these always give us one triangle. If you remember back to geometry, we had the side angle side and the side theorem for showing the triangles that were congruent. That guarantees that we have a unique triangle when we have those combinations. So what I want to do is write down our equations for the two different kinds of triangles. Do a couple of examples, and then we'll talk about again where cosines comes from, and then a new area formula. Now, we don't necessarily have to memorize which case goes with which kind of triangle. You'll have some experience, you'll be able to see. What will happen is if you try to use the law of sines with a side triangle, you realize really quickly that you can't, because you're missing two of the pieces, so it won't work. And the same thing with law of cosines. You'll try to use the law of cosines with one of these triangles, and you're missing some of the information that you need for law of cosines. So that'll tell you, oh, I need to use law of sines for that triangle. All right, so for side angle side triangles. So when we have two sides and the angle between them, the law of cosines tells us that a squared equals b squared plus c squared minus 2bc cosine A. That's the main formula that I remember. The rest of them I'm going to write down are really just rearrangements of the letters. So it's really saying the same thing. We're just rearranging the letters. So we can also say b squared equals a squared plus c squared minus 2ac cosine b, or c squared So all of these are really telling us the same thing. We're just rearranging the letters. A couple of things to notice that help make this easier. Whatever is on this side of the equation, that's the angle that we're taking the cosine of. And the sides on the other side of the equation are all the other sides than this one. So I have a squared on this side. All of my sides are b and c on this side. A on this side, the cosine is on that side. So that's kind of how I think about this one. All right, so let's look at this for a second. If we covered up this term, if we got rid of that, and we just had a squared equals b squared plus c squared, what is that? That's the Pythagorean theorem. If our angle has a 90-degree angle, what if angle A is 90 degrees? What's the cosine of 90 degrees? 0. So I'd have 0 times all of this stuff. So if my angle is 90 degrees, the law of cosines turns into the Pythagorean theorem. The law of cosines really is an extension of the Pythagorean theorem. That's the other way that can help you remember it, is it starts out like the Pythagorean theorem. It actually comes from the Pythagorean theorem. And we'll see that in a little bit. Now for side-side-side triangles. All we're going to do with side-side-side triangles, we don't have any angles, so we need to figure out the angles. So I'm just going to solve each of these for cosine A, cosine B, and cosine C, and then we can use the inverse cosine on our calculator to find the angle. So if I solve these for the angles, I get cosine A and for cosine B, and all I'm doing is solving this for the cosine of B, and then finally for the cosine of C. So that's going to give me my expression for cosine C. Again, really, these are all one formula, just rearranging the letters. But what I recommend is remembering this one, and remembering that you can get your angles just by solving this for the angle. So questions on our formulas. Talk about where they come from in just a second. I just want to do a couple of examples, point out a couple of common mistakes. So let's start out with the side-side-side example. So we know that A equals 5, B equals 8, and C equals 7. And we want to find 3 angles. So I like to draw a picture, and my pictures aren't always to scale here, so be aware of that. This is 7, 8, 5. All right, so here's the first place that it's easy to make the mistake with law of cosines. So we're going to use the law of cosines to find an angle. We want to find, using the law of cosines, find the largest angle first. And the reason that we want to do that is because normally when we use the law of cosines, we use the law of cosines once, and then we'll finish the problem with the law of sines, because the law of sines is easier to use. And once we have one angle here, then we can use the law of sines. If we did not find the largest angle first, and if that largest angle turned out to be obtuse, and we needed to find the angle by using the inverse sine button in our calculator, our calculator will not give us an obtuse angle from an inverse sine when we press the inverse sine button. It will only give us an acute angle. Yes? Have to be, yes, we're going to be in degree mode in using law of cosines, because usually we talk about degrees of time. So our calculator won't give us an obtuse angle when we press the inverse sine button. So let's think about why that would be. So if I draw a little circle, a unit circle over here, and I'm finding I have an obtuse angle here, and I need to find the inverse sine to find the obtuse angle. What's our domain restriction for inverse sine? Negative. And then for the angle, the sine, our domain, the range of the sine function is negative 1 to 1. Our angle for an inverse sine has to be between what two angles? That's for inverse cosine. Negative pi halves to pi halves. So our inverse sine, our angle has to be over here. So what the calculator is doing is saying we're finding this y-coordinate, but my y-coordinate has to be in this quadrant, so it's going to find this angle over here that's in the domain of the inverse sine function, and it's going to find the inverse sine, give you that angle. So our calculator will not give us an obtuse angle when we press the inverse sine button. Because the domain of our restriction for inverse cosine was 0 to pi, the inverse cosine button will give us an obtuse angle. So in case that largest angle is obtuse, we have to use the law of cosines to find that angle, find that largest angle first. All right, so in this triangle, which angle is going to be the largest angle? Angle B, opposite the largest side. So we want to find angle B. So I'm going to use the law of cosines, and it tells me that the cosine of B is a squared plus c squared minus b squared over 2ac. So I get that cosine of b, when I plug in my numbers, is 5 squared plus 7 squared minus 8 squared over 2 times 5 times 7. And b is going to be the inverse cosine of this quantity. So when I calculate that out, I get that this is the inverse cosine of 0.143. When we are using law of sines or law of cosines and we need to find an angle, keep at least 3 decimal places to make your angle as accurate as you can. So this tells me that b equals 81.8 degrees. So in this case it didn't turn out to be obtuse, so we were okay. But if it had turned out to be obtuse, then we would have made sure we found the right angle. Now that we found that angle, 81.8, now we can finish the problem with the law of sines. The law of sines is going to be easier to use than using the law of cosines. There's more going on here than there is in law of sines. Law of sines. So I'm going to finish. Finish with the law of sines. I'm not going to go through the calculations. We've been doing that for a couple of days. So what I would do to set it up is say I want to find angle A. I would say sine A over 5 equals the sine of 81.8 degrees over 7. Find angle A using that, and then the third angle, we know our 3 angles have to add up to 180, so we can find our third angle by subtracting from 180. Did I put my angle in the wrong place? Yes. 81.8. So and then I wrote this sine A, sine 81.8 over 8. There we go. I think when I did this, we taught this lesson twice yesterday. When I did the examples yesterday, made this angle too, and I was thinking that automatically. All right, so we would finish our problem that way. Thank you for pointing that out. All right, questions on that example? So the thing we have to be careful with there: find the largest angle first when we have a side-side triangle. And let's just to emphasize here, we have 3 sides. So this is a side-side triangle. Now someone asked yesterday, was it on this one? Never mind. All right, let's look at another example. So we'll do a side angle side triangle this time. So we know that angle C is 111 degrees. Side A is 27, and side B is 18. We want to solve this triangle. So draw a picture here. On 11 degrees, A is 27 and B is 18. So we have a side angle side triangle here. You can use the law of cosines. Now, before we use the law of cosines, if we try to use the law of sines, I would say C over 111 equals C over the sine of 111 equals sine of A over 27. Well, I don't know C or A, so I'm missing two pieces for the law of sines. I don't know C or angle A. So I'd be missing two pieces for the law of sines. So that would tell me that I couldn't use the law of sines. I need one of those two pieces of information to use the law of sines. So we're going to find side C. So I'm going to say C squared equals A squared plus B squared minus 2AB cosine C. So plug in my numbers. Plus 18 squared minus 2 times 27 times 18 times the cosine of 111 degrees. So here's the other common error in the law of cosines. What is the cosine of 111 degrees? Can someone calculate that for me? The cosine of 111 degrees comes out to be a negative number. So I have a negative number here times a negative out here in front of that expression. So I end up having to add this expression. It's very easy to forget when you have an obtuse angle and you get a negative cosine to multiply those two negatives together and end up adding that term. So that's probably the most common mistake with the law of cosines, is forgetting that we have a negative here, and for an obtuse angle we have a negative there, and we end up adding. So that's the other mistake to avoid with law of cosines. So for this one, I get that when I calculate this out, that C squared is approximately 1404.33. Take the square root, so C is about 37.43. And now I can finish the problem with the law of sines. Using law of sines is going to be much easier than using law of cosines. So just as an example, for example, the way I would set it up is I would say that the sine of 111 over 37.43 equals sine A over 27, and then I could solve for angle A. Once I had angle A, then I could find angle B, because all three of my angles have to add up to 100. So questions on that example? The law of sines not any more complicated than law of cosines, not any more complicated than law of sines. Just a couple different things that we have to be aware of. When we have a side-side-side triangle, make sure you find the largest angle first, and make sure you pay attention when we have an obtuse angle, our cosine is going to be negative, and that turns this entire term positive. We end up adding. All right, let's take a look at where the law of cosines comes from. Knowing y is always a nice thing. So what I'm going to do for this to figure out how law of cosines comes about the way it does is I'm going to put my triangle on my coordinate axis. And I'm going to put angle A, I'm going to write angle A in here. I'm going to write angle B in here. And this is angle C. And so the coordinates, we're going to say the coordinates of this vertex of the triangle are 0, 0. This entire length, side length, the way we've been labeling our triangle is C. So if this side length is C and we're starting here at 0, 0, we know angle A. We're going to say we know angle A. And we know side C. So we have this nice side angle side triangle. We know angle B, or sorry, we know side B, we know angle A, and we know side C. We have a side angle side triangle there. We want to figure out side A. So if this is 0, 0 here at this vertex, what are the coordinates of the vertex here at where angle B is? 0, what is it? C0. There we go. We're going over C units and up 0 units. So that coordinate would be C0. And we're going to call this coordinate just xy. It's just some point up here, xy. So this, put this at 0, 0. This is going to be at C0. And this is at xy. Now we're going to use a trick that we've used over and over with law of sines. Not really a trick, but a technique. Turn this into a problem that we already know how to solve, like a good mathematician, setting our dumpster on fire. And we're going to draw in the height of the triangle. So if this point is xy, what is the length of this side of the right triangle? X. So that distance is x. And what is this distance? Y. All right, so now we have a right triangle, and we have the sides of the right triangle. Now we're set to find our law of cosines. We're going to use a distance formula to find the length of A. And I'm going to say that A is the square root of x2 minus x1 squared plus y2 minus y1 squared. And the distance formula is really what equation in disguise? The Pythagorean theorem. The distance formula really is the Pythagorean theorem. I'm going to square both sides. A squared equals x minus c squared plus y squared. Now let's go back to our triangle. When we were using the law of sines, how do we calculate the height of this triangle? Y equals, we know angle A and we know side B. Gabe? So how have we been calculating the height of our triangle with law of sines? The height of this triangle is going to be, we know angle A and side B. B sine A, right. Y equals B sine A. Using that same idea, how would we find x? This is the adjacent side, and this is the hypotenuse. So x would be b cosine A. Now we're going to substitute these in to our equation. So a squared equals b cosine A minus c squared plus b sine A squared. Well, let's look at this really quickly. I have a sine A squared here, and I have c is the length of this side. So I have a sine A squared and a cosine A that's going to end up being squared here. So what does that make us think of? What is it? The quadratic. What? Sine squared and cosine squared are Pythagorean identity. So we're hoping something's going to come out of that. So let's expand this. So a squared equals, I get b cosine A, quantity squared, and I get two of these multiplied together, so minus 2bc cosine A. Does that look familiar from what we just talked about? Plus c squared from this, plus b sine A, quantity squared. Now I'm going to rearrange things a little bit. So a squared equals b squared cosine squared A plus b squared sine squared A from these two plus c squared minus 2bc cosine A. What can I do here? Factor out the b squared. So a squared equals b squared times cosine squared A plus sine squared A plus c squared minus 2bc cosine A. Cosine squared A plus sine squared A is 1. So I get a squared equals b squared plus c squared minus 2bc cosine A. And there's my law of cosines. Using the Pythagorean theorem, using a little bit of trigonometry, using a trig identity, and we get the law of cosines. Kind of nice. So now this doesn't have to be a mysterious formula that just appears. We have an idea of where it comes from. All right, questions? Okay, last thing. Heron's area formula. So this is our area formula that comes from the law of cosines. So for a side triangle, the area equals the square root, and I'll tell you what S is in just a second. S times S minus A times S minus B times S minus C, where S is A plus B plus C, the three sides of our triangle divided by 2. And this is called the semi-perimeter. So if we have three sides of a triangle, we can use this equation use this formula to find the area of the triangle. So now we have three ways to find the area of a triangle. We have base times height divided by 2. We have our formulas that came from law of sines. Area equals 1/2 BC sine A. And then we have Heron's area formula. It's named Heron's area formula. Greek mathematician Heron was the first one that came up with this formula. And it comes from the law of cosines. Kind of difficult to show how it comes from the law of cosines, so you just have to take my word for it on that. If you only had 3 sides, you could either use this formula, or you would have to do a lot more work to use one of the other formulas. But you could use, if you had a side-side triangle, you could use the law of cosines to find one of the angles, and then you could use the other formula that came from the law of sines, which is that might actually be an easier way to do it. Because this is kind of complicated, but it's nice to know that it exists. All right, questions? Okay, homework. All right, there you go.